Let's now look at the last two questions from the 2018 final exam paper. So question B5, it's dealing with belt drive system. So it says that the belt is running at a speed of 950 meters per minute. The angle embraced by the belt around the pulley is given as 120 degrees. The coefficient of friction between the belt and the pulley is given as 0.35. The width of the belt is 250 mm, whereas the thickness of the belt is 9 mm. So these are very important parameters to take note of. The density of the belt material is given as 980 kg per meter cube. It says that if the maximum stress in the belt is not to exceed 2 megapascal, so that's your stress sigma, and the centrifugal tension, so this is a qualitative information that you need to keep in mind, that we are taking into account the effect of centrifugal tension in our calculation. So you are to determine the maximum tension in the belt, right? The centrifugal tension, the tension in the belt, that is T1 and T2, the power that can be transmitted by this belt drive system, and finally the velocity for maximum power transmission. So as I mentioned earlier, we need to identify the values, the parameters that are given to us in the question, as well as looking at the qualitative information that is given. So one of the things that you need to keep in mind is that we are taking into account the effect of centrifugal tension. Belt width and thickness is 250 and 9 mm respectively. The belt is rotating at a speed of 950 meters per minute. So now let's look at the maximum tension. Your maximum tension T is nothing but the total tension on the tight side, which is simply given as sigma I. Right, so your maximum tension is nothing but the total tension on the tight side, and it is given by sigma I, and I is the cross-sectional area. In this case it is just width of the belt times the thickness of the belt. So the maximum stress was given as 2 megapascal, should not exceed 2 megapascal. Width was width was given as 250 mm, so 0.25, and the thickness was 9 mm. So you get your maximum tension in the belt to be 4500 newtons. Now the next thing is we have to calculate our centrifugal tension, and Tc is given by mv squared. For this we need to find our mass of the belt as well as the velocity. So in the question, the velocity of the belt, or the speed at which the belt was rotating, was given as 950 meters per minute, and we know that the velocity has to be in meter per second. So basically it is 950 meters per minute. So a minute has 60 seconds, so just basically divide 950 by 60 seconds, so you get a value of 15.83 meter per second. We know that the mass of the belt is given by density times the volume, and volume is nothing but the cross-sectional area times the length of the belt. So density, this is basically calculating the volume of the belt, which is cross-sectional area, B times T times the length, and we take our length to be 1 meter. So density was 980, width was 250 mm, thickness was 9 mm, and we take the length of the belt to be just 1 meter. So we get our mass to be 2.2 2.205 kg, and your centrifugal tension Tc is mv squared. Substituting the values of mass and velocity into the equation, you get your centrifugal tension to be 552.55 Newton. Now part 3 of the question says that you have to find the tension in the belt, that is basically T1 and T2, and in order to do this we have to find our tension ratio. So according to the question, the angle of embrace was given as 120 degrees. Converting that to radians, you get 2.09 radians, and the tension ratio T1 over T2 is equals to exponential mu theta. Coefficient of friction was 0.35, radians is over here, so you get your tension ratio T1 over T2 to be 2.08. Now what happens is, this is something very important that you need to understand. So it says that your total tension on the tight side is simply equals to T1 plus Tc, and Tc is your centrifugal tension, and Tt1 is same as your maximum tension over here. So these two parts are interrelated. So T1 was 4500, so 4500 is equals to T1 plus Tc, and Tc we had calculated over here. So 4500 minus 552.55 gives you your T1. T1 is 3947.45 Newton, and using the tension ratio T1 over T2 we get our T2 to be basically 1897.81 Newton. Finally, it says you have to find the power that is transmitted by the belt. Power is simply given as T1 minus T2 times the linear velocity. So T1 minus T2 times your velocity, you get the power transmitted to be 32.45 kilowatt. And the last one was to find the maximum velocity taking into account maximum power transmission condition. So for that, your maximum velocity is simply square root of T over 3m. So your maximum tension from here, mass over here, so substituting, you get your maximum velocity to be 26.08 meter per second. So the maximum power will be transmitted when the belt is run at a speed of 26.08 meter per second. So again, you have to be very careful as to what the question is asking. Again, here it is sigma times cross sectional area. If you given a rope drive system or a circular belt drive system, so you need to take into account that in that case the cross sectional area will be pi r squared. If you given a V belt, then V belt will specify cross sectional area, or maybe dimensions are given so that you can find the cross sectional area. So be very careful, don't use this step blindly. This is a general formula that is going to be true always, but once you convert it over here, in this case B times T, because the cross section was basically a rectangle, so in that case I can do width of the belt times the thickness of the belt to get my cross sectional area. So this is where students make mistake. Over here it's 950 meters per minute. So again, we know that your velocity has to be in meter per second, so don't forget to convert over here. In this formula, length of the belt is taken as 1. Moving on moving on to the last question, which is looking at question 6. As shown in the figure, you have a rectangular steel bar which is cantilevered to a steel channel. So this is your bar and this is your channel, and it is held in place using 6 M12 bolts. So M12 means the diameter of the bolts are 12 mm, located at A, B, C, D and E. And then what happens is a applied load of 30 kilonewton is given. So for this particular scenario, we have to find the resultant load in each bolt. So what the resultant load is, that you have to find the resultant forces acting in bolts A to F. We have to find the maximum shear stress in the bolt, and then finally the maximum bearing stress. So what happens is, the manner in which we solve this problem, the first thing that you need to do is you need to draw the free body diagram of the forces acting on each of these bolts. So what happens is, in this case you can see that the bolts are separated at a distance of 80 by 80 mm, so it's a perfect square. So what I have is, I've got my bolts A, B, C, D, E and F, and in this I'm representing my primary and secondary shear. So primary shear is in the same direction as your load. So in this case the applied load is acting downwards, so you'll see that primary shear is acting downwards on all of these bolts as such. So these are your primary shear. Now the second thing is, how do I represent this secondary shear? And what happens is, again referring to your lecture notes and then looking at the tutorial video, I was quite clear. What happens is, the first thing is you have to identify your centroid. So the centroid of this bolt pattern is located right at the center over here. So now what happens is, with respect to the centroid, you see in which direction is this global moment. So when you look at this to be your centroid over here, this to be your centroid, this 30 kilonewton is going to cause a moment which is in the clockwise direction about the centroid. So the global moment is clockwise about the centroid, so centroid is over here. so global moment is clockwise. So on these lever arms I have to represent forces on this lever arm such that it also represents a moment which is clockwise about this centroid. So your moment has to be in the clockwise direction. So what happens is moment is force times perpendicular distance. So in this case you'll see that this is your lever arm from, let's say, O to I. O to I, this is your lever arm. So this secondary force has to be 90 degrees to this lever arm. So 90 degrees is over here, and we need to ensure that the moment is clockwise as well. So you'll see that this arrow is in this direction, so this causes a clockwise moment. Now looking at this head B, so this is your lever arm, which is just a vertical line joining O to B and O to E. So 90 degrees is over here and clockwise, so this is why you see the secondary force is acting from left towards your right, so clockwise moment. Over here again clockwise moment, 90 degrees, 90 degrees, and so on. So that's how you will represent your secondary shear. So this is just representing your primary and secondary shear on these 6 bolts. We haven't started with the solving part yet. Now what happens is I can find my secondary primary shear. Primary shear is simply given as V over N. V is the load that is applied and N is the number of bolts that is used. So in this case what I have done is I have said that primary shear on all the bolts are going to be same. So 30 divided by 6, you get 5 kilonewton. Okay, so that's your primary shear. Now the next thing is I can find the distance of each bolt from the centroid. So centroid is right at the center over here. So right at the center over here. So now what we do is we find the distance of each bolt from the centroid. So for RA, basically when we look at RA over here, RA, this is 80 in the horizontal direction, and vertical direction is also 80 mm. So we can find the distance. So it's 80 squared plus 80 squared whole thing square root. So we get a distance of 113.14 mm. So bolts A, C, D and F are located at a distance of 113.14 mm from the centroid. And when we look at bolts B and E, they are simply located at a distance of 80 mm from the centroid. Done. The next thing is we can calculate our moment, which we will later use to calculate our secondary shear. So your moment is force times the distance, and this distance is basically the distance of the applied load, which is 30 kilonewton from the centroid. So your centroid was over here. This is where your centroid is. So distance of the applied load from the centroid is basically 850 plus this gap is 50, right? So that's 900 and then another 80. So the distance of the applied load from the centroid is 980 mm. So simply we get our moment to be 29,400 Newton meter. So this is just finding some fundamental quantities before we start solving the problem. And then what happens is this alpha is tan inverse of opposite over adjacent. So in this case even I can find my alpha over here. So it's tan inverse of 80 over 80, which is basically 45 degrees. So these angles over here, this angle, all these angles over here are 45 degrees. So what we'll do is, the next thing is, after finding our primary shear, we'll find our secondary shear. So secondary shear on bolt I is simply given as moment times the distance of bolt I from the centroid, which is simply RA, divided by 4 times RA squared plus 2RB. So okay, I'll explain as to why I have got 4 times RA squared. Over here in the denominator, what you'll have is you will have RA squared plus RB squared plus RC squared plus RT squared plus RE squared plus RF squared. But you'll see that the distance of bolt I, bolt C, bolt D and bolt F from the centroid over here are the same. So RA, RC, RD and RF are same as the given over here, right? So what I can do is I can simply say 4 times RA, right? So 4 times Ra squared, and then what you can do is, if you look at this diagram over here, distance of bolt B and bolt E is same from the centroid. So this was 80 mm, so basically 2 times Rb squared. So substituting everything, you see that your secondary shear on bolts A, C, D and F are 51.97 kilonewton. Now again, it's common sense. If the distance of the bolts are same from the centroid, it basically means that the secondary shear acting on that bolt is same, because what I can do is I can say secondary shear on bolt C is simply MRC divided by 4Ra squared plus 2Rb squared, but you already know that Ra, Rc, Rd and Rf are same. So if the radius of the distance of the bolts from the centroid are the same, basically the secondary shear is same. So this is why I have this over here. And then finally, secondary shear on bolt B is same as secondary shear on bolt E, because the distance of bolt E and bolt B from the centroid is the same. So basically this is what I have, and then I get my secondary shear on bolt B and E as 36.75 kilonewton. You will notice that what I'm doing is I'm using the units here in mm, right? So you've got 113.14 mm, but at the same time you'll see that instead of using my moment, which was 29.4 kilonewton, in that form I'm using 29,400. So in that sense this equates to these values, but for me I would advise you that you use everything in SI units. Now the next thing we'll do is we'll look at the resultant force acting on each bolt. So the first thing is we'll find the resultant force acting on bolt A. So the resultant force Fi is basically the vector sum of F primary shear at bolt A plus the secondary shear at bolt A. So what we do is, for this we will use our cosine rule. So cosine rule states that Fi squared is equals to F prime A squared plus F double prime A squared minus 2 F prime A to double prime A cos theta. So this is your primary shear, this is your secondary shear, and this cos theta is the angle over here. So again, very simple, we knew that this angle is 45, so this forms a 90 degree over here. So theta is also equals to 45 degrees. So substitute all these values over here and you'll get a value of 48.56 kilonewton as your Fi, and Fi is same as Ff. Looking at this diagram, when you look at this diagram over here, Fi is same as Ff. Now looking at Fb, again what I can do is I can start with my cosine rule, but I'm straight away using my Pythagoras theorem. The reason is the angle over here is 90 degrees. So whenever I do cos of 90, I simply get 0. So if I had to write Fb squared is equals to F prime B squared plus F double prime B squared minus 2 F prime B times F double prime B cos theta. So this cos theta over here would have been 0. So all of this term for this would have been 0. So I would have only been left with F prime B squared plus F double prime B squared, which is equals to Fb squared. So in that sense, when I solve for Fb, I simply get 37.09 kilonewton. So since this is at 90 degrees here, I can straight away use my Pythagoras theorem. Now looking at force, the resultant force acting on bolt C. So again, resultant force Fc is basically the vector sum of primary shear plus secondary shear. So again, this is my cosine rule. This time around I have to be careful regarding my angle theta here. So quite easy, this is 90 degrees, so done. You can see that this angle is also 90 degrees over here. We know that this angle is 45, so this this angle is 45 over here. So this angle is 45, so 90 plus 45 is 135. Substituting for the values, you get the force acting on bolt C, the resultant force acting on bolt C is 55.62 kilonewton. Force acting on bolt C is also same as the resultant force acting on bolt D. So FC is same as FD. And lastly, what we have to do is we have to find the maximum shear stress and maximum bearing stress. So your tau max is equals to F max over I, and F max is the maximum force that acts on these bolts, and we found that the maximum force was acting on bolt C and D, which was 55.62 kilonewton. When we finding our shearing stress, for shearing stress, it is basically the cross-sectional area that we're looking at is a circle basically, and that is given by pi d squared upon 4, and the diameter of the bolt was given as 12 mm. So substituting for these values here, your maximum stress or shearing stress is 491.79 megapascal. When we look at the bearing stress, your bearing stress sigma b is given by F max over I. In this case, what we have is bearing stress is this area that we're looking at as per your lecture notes. So what happens is, this is the area that you're looking at, and if you look from the top, what we have is we basically have this distance as the diameter of the bolt, and this distance as the thickness of the thinnest member that we have. So the thickness of the thinnest member, when we look at the two members here, which is the cantilever beam and the channel, the member which has the smallest thickness is the channel, which is 20 mm. So this is what we have. Diameter of the bolt was 12 mm and the thickness of this member is 20 mm. So this is how I calculate my bearing area. So basically your bearing stress is nothing but 231.75 megapascal. So that basically brings us to the end of the discussion for our 2018 final exam paper. If you have any questions, do not hesitate to ask. Thank you.